Today, we studied section 2.4 and 2.5. I combined these two sections to present. Today, I introduce you 3 types of limit: infinite limits, limits at infinity, and infinite limits at infinity. Here are the definitions of these limits. Number A, if Sx approaches some finite point A, function approaches either positive infinity or negative infinity, then the limit is an infinite limit. Example 1, this is an infinite limit. As x approaches A is a finite point, from the left side, function approaches negative infinity. The graph of this function looks like this curve. Near the point A from the left side, the graph down to negative infinity. This vertical line is a vertical asymptote of the graph. Example 2. This is an infinite limit. As x approaches the point A, both-sided, function approaches positive infinity. The graph of this function looks like this curve, this blue curve. Near the point A, both-sided, the graph up to positive infinity. Again, this vertical line is a vertical asymptote of the graph of the function. B, if Sx approaches positive infinity or negative infinity, the function f approaches some finite number, then the limit is a limit at infinity. Here are 2 examples. Example 1, this is a limit at negative infinity. As x approaches negative infinity, function approaches L. L is a finite number. The graph of the function f looks like this blue curve, And this horizontal line, L, is a horizontal asymptote of the graph of the function. Example 2, this is a limit at positive infinity. As x approaches positive infinity, the function approaches some finite number. The graph of the function is this blue curve. Okay, as x approaches positive infinity, the curve gets closer and closer to the number L. This horizontal line is a horizontal asymptote. C, if Sx approaches positive infinity or negative infinity, the function approaches either positive infinity or negative infinity, then the limit is an infinite limit at infinity. Here is one example. This is an infinite limit at positive infinity. As x approaches positive infinity, the function approaches negative infinity. The graph of the function looks like this blue curve. As x approaches positive infinity, the curve down to negative infinity. In this case, the graph has no horizontal asymptote, no vertical asymptote. Here are some examples about the 3 types of limit. Example 1. Sketch a possible graph of a function f together with vertical asymptotes, satisfying all the following conditions on the interval 0 to 4. On the interval 0 to 4, that means that we just need to sketch the graph over the interval 0 to 4. We don't need to sketch the graph outside the interval. Condition 1. Function value at 1 is 0. Yeah, this point is a solid point. Solid point means part of the graph. Condition 2. Function at 3 is undefined. That means that at the point 3, the graph has an open dot. Open dot means the point is not part of the graph. Condition 3. As x approaches the number 3 both-sided, function approaches 1. Suppose this height is 1. As x approaches 3, either from the left or from the right, the graph approaches 1. Condition 4. As x approaches 0 from the right side, function approaches negative infinity. This is an infinite limit. As x approaches 0 from the right side, the graph down to negative infinity. Condition 5, number 5. As x approaches the number 2, function approaches positive infinity. This is an infinite limit. 2 here, x approaches 2 from either side. The graph up to positive infinity. This vertical line is a vertical asymptote. Condition number 6. As x approaches 4 from the left side, function approaches positive infinity. Again, this is an infinite limit. X approaches 4 from the left side, the graph up to infinity. This vertical line is a vertical asymptote. Please note that this is not the graph of a function. For a function, one x value has only one y value. Take a look at this diagram and consider this point. This point is about 3.7. At x is 3.7, I can see there are two y values. This height is one y value. And then from here to here, this height is the second y value. So therefore, this diagram is not the graph of a function. We need to modify this diagram with a single curve. Yeah, here. Okay, now this is the graph of a function. Now let me double check with the conditions. Condition 1, function value at 1 is 0. Let me see. When x is 1, function is 0. Yeah, this point, the height is 0. Correct. Condition 2, function at 3 is undefined. At 3, low solid point. Yeah, at 3, low solid point, only open point. As x approaches 3, function approaches 1. As x approaches the number 3, the curve approaches 1, approaches this open dot. This open dot, the height is 1. Correct. As x approaches 0 from the right side, function approaches negative infinity. As x approaches 0 from the right hand side. The graph down to negative infinity. Yes, correct. This vertical line, the y-axis, is a vertical asymptote. Now, the next two conditions. As x approaches to, this is a both-sided limit, function approaches positive infinity. As x approaches 2 from either side, the graph up to positive infinity. Correct. And this vertical line is a vertical asymptote. Finally, as x approaches 4 from the left-hand side, function approaches positive infinity. As x approaches 4 from the left side, the graph up to positive infinity. Correct. So this vertical line is a vertical asymptote. Example 2. Find these two limits by a numerical method, then by an analytical method. This is one example about infinite limits. That is, the limit is an infinity. This is the solution to part A. In this solution, I have made two tables for the limits. This table is for this left-hand side limit, and this table is for this right-hand side limit. From this table, as x approaches the number 3 from the left side, the numerator of the function, 2x, approaches the number 6. Denominator of the function, 3 denominator of the function approaches 0. The function numerator over denominator approaches positive infinity. So the left-hand side limit is positive infinity. Because the limit is infinity, this limit is an infinite limit. Now, this table, x approaches the number 3 from the right side. Numerator of the function approaches 6. Denominator approaches 0. The function approaches negative infinity. So right-hand side limit is negative infinity. Because the limit is negative infinity, this limit is an infinite limit. A possible graph of the function is this, the blue curve. As x approaches 3 from the left side, function approaches infinity. As x approaches 3 from the right side, function approaches negative infinity. This vertical line is a vertical asymptote. Part B. Find the limits by an analytical method, that is, by limit laws. Again, I only focus on limit law number 8, direct substitution. Consider the left-hand side limit first. To find this limit by direct substitution, plug in the number 3 in x. Then this limit is this number. This number is 6 divided by 0. A non-zero number divided by 0 should be infinity, either positive or negative infinity. Now, to determine the sign of the infinity, I pick a point very close to the number 3, but on the left side. Say I pick 2.99, and then evaluate the function value at 2.99. This is the function. Okay. The function value at 2.99, I plug in 2.99 in x, then the function value is 598, greater than 0. So when x is very close to the point 3 from the left, function value is positive. Therefore, this limit should be positive infinity. Similarly, to find the right-hand side limit, plug in the number 3 in x. Okay, then we have this equation. This number is 6 divided by 0. Non-zero number divided by 0 should be infinity, either positive or negative. To determine the sign of the infinity, now this time I pick a point very close to the number 3, but from the right side. Say I pick 3.01 and then compute the function value at 3.01. Then I get function value is negative 602, less than 0. So when x is close to the number 3 from the right, function value is negative. Therefore, this infinity should be a negative infinity. So we have this result. Example 3. Find these two limits. The functions in the limit are similar, but different. Here is minus, and here is plus. Here the coefficient is 8. Here the coefficient is 6. You can use tables to find the limits, but I prefer to use direct substitution. Now, part A. This limit is a right-hand side limit at -2. To find the limit by direct substitution, we just need to plug in -2 in x. Then the limit is this number. This number is -44 over 0. A non-zero number divided by 0 should be infinity, either positive or negative infinity. Now, to determine the sign of the infinity, we pick a point very close to -2, but on the right side. Say, pick -1.99 and evaluate the function value at -1.99. The function value is positive. So when x is very close to -2 and on the right side, function value is positive. So this infinity should be a positive infinity. So the limit is positive infinity. Here is a possible graph of the function. X approaches -2 from the right side. The graph is going up to infinity. So this vertical line is a vertical asymptote. Part B. The limit is again a right-hand side limit at a point -2. But the function is slightly different from the function in part A. To find this limit, we use direct substitution. Plug in -2 in x, then the limit is this number. This number is 0 over 0. We cannot tell what is 0 over 0. 0 over a non-zero number, we are sure it is 0. A non-zero number over 0, we are also sure it is infinity. Only this case, 0 over 0, we cannot tell what is it. Now, to find the limit, we simplify the function. The function is a polynomial over a polynomial. So we use factorization to simplify this function. Okay, factor out the top and the bottom, then we have this equation. Now cancel x plus 2 from the top and from the bottom. Cancel 1x from the top and from the bottom, then we have this equation. Now to find this limit, direct substitution again, plug in negative 2 in x, then the limit is this number. Now this time, this number is 1 over 8. Therefore, this limit is 1 over 8. Here is a possible graph of the function. When x approaches negative 2 from the right side, the curve approaches this open dot, this point. This point height is 1 over 8. Because the graph doesn't approach infinity, so this time, this vertical line is not a vertical asymptote. Example 4. Find these two limits. This one is a limit at positive infinity, and this one is a limit at negative infinity. The functions in these two limits are equal, are the same function. Now, find the limits by a numerical method, namely by tables. Then by an analytical method, by direct substitution. Then determine the horizontal asymptotes of the function. Here is the solution to part A. To find this limit, I make this table. From the table, we can see that as independent variable x approaches infinity, the numerator of the function approaches infinity. Denominator also approaches infinity. But the function approaches some finite number. This number is the answer of this limit. About the limit at negative infinity, I make this table. From the table, as x approaches negative infinity, the numerator approaches positive infinity. Denominator also approaches positive infinity. But the function approaches some finite number. It seems that this number and this number the same number. So as x approaches negative infinity, the limit of the function is this number. Part B. Find the limits by an analytical method, namely by direct substitution. For this limit, the limit at positive infinity, I plug in infinity in x to get this equation. But how to evaluate this quantity, this quotient? From the table in part A, we saw that as x approaches positive infinity, the numerator approaches positive infinity, and the denominator approaches positive infinity. So this guy is infinity, and also this guy is infinity. But what is infinity divided by infinity? We don't know. A final number divided by infinity is 0. infinity divided by a finite number is infinity. But infinity divided by infinity, we don't know what is that. To determine the limit, we need to simplify the function, or we need to write the function into a form from which we can tell the limit easily. Because the limit is a limit at infinity, I don't use factorization to simplify the function. Instead, I take out the highest power. The highest power in the numerator is x squared, so I take x squared out. The highest power in the denominator is x squared. I also take this x squared out from the denominator. Then we have this equation. Now, cancel x squared from the top and from the bottom, then we have this equation. Now, this limit should be easy to tell. As x approaches infinity, 1 over x approaches 0. 2 over x squared approaches 0. Similarly, 4 over x squared approaches 0. And 1 over x squared approaches 0. Here there is a typo. 1 over x should be 1 over x squared. So as x approaches infinity, this function, approaches this number. This number is 3 over 7. Therefore, this limit, as x approaches positive infinity, the function approaches 3 over 7. Yeah, this infinity over this infinity is 3 over 7. Here is a remark about this solution. Have you noticed that the number 3 is the leading coefficient of the polynomial in the numerator, and the 7 here is the leading coefficient of the polynomial in the denominator? In general, the following is true. For a limit at infinity, where the function is a polynomial over a polynomial, and these two polynomials, they have the same degree, just like here, degree is 2, then the limit is the leading coefficient of polynomial p over the leading coefficient of polynomial q. In general, this is true. Similarly, to determine this limit, a limit at negative infinity, by direct substitution, plug in infinity in x, then we have this equation. But what is this quotient? From the table in part A, as x approaches negative infinity, the numerator approaches positive infinity, and the denominator also approaches positive infinity. So this guy is positive infinity, and this guy is negative infinity. But again, infinity divided by infinity, we don't know what is that. Now, to determine this limit, we need to simplify the function. Again, we take out the highest power from the numerator and from the denominator. The highest power in the numerator is x squared. We take x squared out. The highest power in the denominator is x squared. We take x squared out. Then we have this equation. Cancel x squared, then we have this equation. Now, this limit should be easy to tell. As x approaches negative infinity, 1 over x approaches 0. 2 over x squared approaches 0. 4 over x approaches 0. And also 1 over x squared. Again, a typo. Here should be 1 over x squared. 1 over x squared approaches 0. So this limit is this number. This number is 3 over 7. So as x approaches negative infinity, the function approaches 3 over 7. Namely, this infinity over this infinity is 3 over 7. Here is a possible graph of the function. This horizontal line, the height is 3 over 7. From part B, as x approaches positive infinity, the function approaches 3 over 7. So the graph of the function as x approaches positive infinity, the graph of the function is getting closer and closer to this horizontal line. And also from the part B, when x approaches negative infinity, function approaches the same number 3 over 7. So as x approaches negative infinity, the graph of the function is getting closer and closer to this horizontal line. So this horizontal line is a horizontal asymptote of the function. The equation of this horizontal line is y equal to 3 over 7. All the points that satisfy this equation together is this horizontal line. Example number 5. Find this limit. This is a limit at positive infinity. The function is a polynomial over a polynomial. These two polynomials have different degrees. The degree on the top is 2, and the degree at the bottom is 3. As x approaches positive infinity, 1 minus x squared should approach negative infinity. And x to the third minus x plus 1 should approach positive infinity. Because the degree at the bottom is 3. The degree at the top is only 2. So as x approaches positive infinity, the polynomial at the bottom should go to infinity faster than the top goes to infinity. So their ratio, this ratio should approach 0. This is my inspection. Now, to find this limit, I can see there are 3 solutions. Solution 1, you can use a table to find the limit. Solution 2, we can use direct substitution to find the limit. First, let me write the polynomial on the top into a polynomial of degree 3 by adding this term. Now, the two polynomials, they have the same degree. To simplify this function, I take the highest power out. The highest power on the top is x to the third. I take x to the third out. And the power at the bottom is x to the third. I take it out. Then cancel x to the third from the top and from the bottom. We have this equation. Now this limit is easy to tell. By direct substitution, plug in infinity in x, then we get this equation. 1 divided by infinity is 0, so this quotient is this number. This number is 0. Therefore, as x approaches infinity, this function approaches 0. The third solution, we can use the remark in the last example to find the limit. The limit is a limit at infinity, and the function is polynomial over polynomial. Write the polynomial on the top into a polynomial of degree 3 by adding this term. Now the two polynomials have the same degree. So by the remark in the last example, this limit is the leading coefficient on the top over the leading coefficient at the bottom. So the limit is 0 over 1. So 0. So as x approaches infinity, this function approaches 0. Example number 6. Find these two limits. The limit in part A is a limit at positive infinity. The limit in part B is a limit at negative infinity. The functions in these two limits are equal. They are the same function. Now, in this example, I am going to find the limits only by analytical method. Solution to part A. To find the limit, let me simplify the function into a function from which we can tell the limit easily. In the numerator, 2x squared plus 1, the highest power is x squared. So I take x squared out to get this factorization. In the denominator, 3x minus 5, the highest power is x. I take x out to get this factorization. Now, I move x squared outside the square root. Please note that when we move x squared outside a square root, remember to add an absolute value on x to make sure this guy positive. For example, when we take square on positive 3, then take square root. From a calculator, the answer is positive 3. However, when we take square on negative 3, then take square root. From a calculator, the answer is also positive 3 rather than negative 3. So when we cancel square and square root in this case, don't forget to add an absolute value on negative 3 to make sure this number is positive. because x is approaching positive infinity, x is positive. So absolute value on x is x itself. Therefore, we have this equation. Now, cancel x from the top and from the bottom. We then have this equation. This limit now should be easy to tell. As x approaches infinity, 1 over x squared should approach 0. 5 over x should approach 0. So as x approaches positive infinity, this function should approach this number. This number is square root of 2 over 3. So this limit is square root of 2 over 3. Solution to part B. The limit is a limit at negative infinity. X is approaching negative infinity. To find the limit, again, I simplify the function. I factor x squared out in the numerator and factor x out in the denominator to get this equation. Then I move x squared outside the square root. When we move x squared outside a square root, don't forget, add absolute value on x. Now, because x is approaching negative infinity, x is negative. Absolute value of x is positive. X is negative. To make them equal, we need to add a minus sign in front of x. X is negative. Negative x is positive. For example, negative 7 is negative. Absolute value of negative 7 is positive. Now, to make absolute value of negative 7 and negative 7 equal, we need to add a minus sign in front of negative 7. So we have this equation. Now, cancel x from the top and from the bottom. We then have this equation. Now the limit, this limit should be easy to tell. As x approaches negative infinity, 1 over x squared should approach 0. And 5 over x should approach 0. Therefore, this function approaches this number as x approaches negative infinity. This number is negative square root of 2 over 3. This is the limit of this function as x approaches negative infinity. Here is a sketch of the graph of the function. From part A, when x approaches positive infinity, the function approaches this number. So the graph is getting closer and closer to this horizontal line. This horizontal line is a horizontal asymptote of the graph of the function. From part B, when x approaches negative infinity, the function value approaches this number. So the graph approaches this horizontal line. This horizontal line is a second horizontal asymptote of the graph of the function. So the function in this example has two different horizontal asymptotes. This horizontal asymptotes equation is this equation. And this horizontal asymptote, the equation is this equation.